Welcome to Lesson 38, where we will balance chemical equations by adding coefficients to make sure matter is not created or destroyed. Today, we're going to review how to balance chemical equations. When balancing chemical equations, we add coefficients to chemical reactions in order to ensure that both mass and charge are conserved. When looking at conservation, it's important that we remember that both matter and energy cannot be created or destroyed. In chemical reactions, matter is not created or destroyed, but instead it is rearranged as bonds are either formed or broken. In all chemical reactions, mass, charge, and energy are conserved, meaning the mass, charge, and energy of the reactants to the left of the arrow are always equal to the mass, charge, and energy of the products to the right of the arrow. Let's take a moment to look at this chemical reaction where water is formed from its elements hydrogen and oxygen. Recall that the reactants occur to the left of the arrow, so the reactants are hydrogen, a diatomic element, and oxygen, another diatomic element. And this arrow reads forms, creates, or yields, and it makes water. Now when we look at this picture, we can see that we have 4 atoms on the reactant side, but only 3 atoms on the product side. If we assign a mass to the atoms, we'll see that we have a mass of 34 on the reactant side. That's found because the mass of hydrogen is 1 and the mass of oxygen rounds to 16.0. But on the product side, we now only have a total mass of 18. So here we've lost mass. So what we're going to need to do is add coefficients or multiples of certain parts of this chemical reaction to make sure that matter and mass are conserved. So here you can see that we first start by adding a coefficient of 2 to the water. This coefficient of 2 adds another oxygen. When I have 2 waters, I have a total mass of 36. And then when I go and if I have 2 waters, I'm also going to need 2 hydrogen molecules. So I add the coefficient of 2 to the hydrogen molecule. And so when I add the masses up on the reactant side, I have 32 due to the oxygen, plus 4 more, 36 total for the reactant side. So again, on the reactant side, the total mass now is 36 grams per mole. And on the product side, I also have a total mass of 36. So here I can see the mass is conserved. I can also simply just look at the atoms and see that I have 4 open circled hydrogens and 2 closed circle oxygens on both sides of the reaction. Before we start balancing chemical reactions, it's important to remind us why chemical reactions occur. Chemical reactions in nature are favored when the products have lower energy and greater disorder than the reactants. We know that the entropy or disorder is related to the phase of matter, as solids have very low energy or disorder as their particles vibrate in a fixed geometric pattern, while gases have the most entropy as their particles are in constant random straight line motion. There are 3 ways in which we can increase entropy. We can change the phase, we can create gas. So here in this chemical reaction where solid zinc reacts with aqueous hydrochloric acid, you can see that we are producing hydrogen gas. So this reaction begins with no gas on the reactant side and ends with gas being produced on the product side. The final way to increase entropy is to dissociate or dissolve something into water. We know that when ions form, they dissociate into water. They separate into their individual charges in water and create an electrolyte solution. So here you can see the dissociation of an ionic compound and a covalent compound. In the ionic compound, salt, you can see that the individual ions, represented by these blue and green particles, separate. While in a covalent compound, the particles separate from the bulk, but they don't separate from the molecule. So the entire molecule remains intact, just is surrounded by water. So this is really important because ionic compounds form electrolytes because they have these free moving ions or charges in a solution. But since covalent compounds, although they separate, they have no charges to them as they are sharing electrons to obtain stable noble gas valence electron configuration, which is a charge of 0, they are non-electrolytes. Here is a Regents question that has us examine entropy. Every time we see the word entropy, we should replace this word with disorder. So we are looking for the lowest disorder or the most organized substance. Now, the formula is not important here, but what is important is the phase of matter. Since we have two liquids, we know that neither liquid could be the answer. Now, the most organized phase is always the solid phase. In addition to favoring reactions with higher entropy, recall that nature favors reactions that release energy or are exothermic. To find the value of salt that releases energy, look up the delta H's on table I. The negative delta H, which corresponds with lithium bromide, is the one that releases energy as it dissolves. This reaction asks us to look at reference table I, heats of reaction. We can look at reference table I or simply look at the reaction. You can see the heat term comes after the arrow. It is on the product side. When heat is on the product side, heat is released, making this reaction exothermic. On reference table I, the bottom footnote reminds us that the negative sign for the delta H indicates an exothermic reaction. So choice 1 is the best choice. Here are the steps to balancing a chemical equation. Balancing chemical equations is difficult and is not straightforward, but using a system, you can do this. So the first thing you want to do is make sure that the chemical equation is written correctly. This step will always be done for you. The next step is to count the number of atoms on both sides of the equation. I personally prefer to make a chart, but you can also use pictures. When I make my chart, I like to write the element symbols directly below the reaction arrow. Red atoms are magnesium, blue atoms are hydrogen, and the black atoms are chlorine. Now we have to count the number of each element on each side of the reaction. There is 1 magnesium, 1 hydrogen, and 1 chlorine on the reactant side. But on the product side, there is 1 magnesium, there are 2 chlorine, there are also 2 hydrogen. So we can see that although the number of magnesium is balanced or the same on both sides, the number of hydrogen and chlorine are not. To remedy this, we need more hydrogen and chlorine. This can be done by adding the coefficient of 2. Adding a coefficient of 2 adds another hydrogen chloride, which always looks like 1 hydrogen bonded to 1 chlorine. After I add the coefficient of 2, I need to update my chart to reflect that I now have 2 hydrogens and 2 chlorine. I have the same number of atoms of each element on both sides. Now the equation is balanced. You may use pictures or a chart, but try and balance the next formula for the formation of ammonia. Did you get this answer? If you did, that's great. If not, try again. If you're still having trouble, please come to class with questions or go to tutoring. Remember, when balancing chemical equations, we are only adding coefficients. We are never changing the subscript. Changing the subscript changes the compound, which we know will change the properties. Here is a description of 4 tricks to balancing. Again, today we're going to balance in both pictures and with a chart. You can pick the technique that works best for you. In this reaction, we begin with aluminum. We'll make aluminum a red element. On the reactant side, there's 1 aluminum, and on the product side, there are 2. And oxygen. Here, we'll make oxygen blue. On the reactant side, there are 2 oxygens. On the product side, there are 3. Now we have to record those numbers in our chart. So we have to pick an element to balance first. Sometimes when balancing, it won't always be straightforward. Let's begin with the aluminum. To balance the aluminum, I'm simply going to add another aluminum. Now I have 2 aluminums. So I'll update my chart and add a coefficient. Now I need to balance the oxygens. The oxygens on the reactant side are in multiples of 2, and on the product side are in multiples of 3. To find the least common multiple between 2 and 3 is 6. To make 6 oxygens on each side, I will multiply the reactant side by 3 and the product side by 2. Let me update the pictures and the chart. So 3 O2s are 3 sets of diatomic oxygen. That gives 6 oxygen atoms on the reactant side. Now, to get 6 oxygen atoms on the product side, I have the coefficient of 2 on aluminum oxide. Aluminum oxide always has 2 aluminum atoms and 3 oxygen atoms. So notice I do have 6 oxygen atoms on the product side, but I've changed the number of aluminum atoms I had. Now I have a total of 4 aluminum atoms. See the 4 red elements? So that means I'm going to have to go back and adjust the coefficient for aluminum. To adjust the coefficient for aluminum, I'm going to change the 2 to a 4. By adding a coefficient of 4, I'm adding 2 more aluminum. Now I have 4 aluminums on the reactant side and 4 aluminums on the product side. Now my equation is balanced. Again, it's important to note that sometimes balancing requires steps, and you have to retrace your steps and try again. The next trick I'll show you in balancing is called the polyatomic ion trick. One easy way to find polyatomic ions in formulas is to look for parentheses. The other way is to look for 3 or more elements bonded together. When balancing with polyatomic elements, you can distribute and count the elements individually, or, as I recommend, keep the polyatomic ion together and count it as a single unit. So when considering a compound like silver nitrate, instead of counting the atoms individually, where there is 1 silver, 1 nitrogen, and 3 oxygens, I can simply count 1 silver and 1 nitrate. In aluminum carbonate, there are 2 aluminums and 3 carbonates, while in iron 3 nitrate, there is 1 iron and 3 nitrates. Let's see if we can show this formula in pictures. Now that we have the pictures drawn, let's count the number of elements on both sides of the reaction. It's always a good idea to divide the reactants from the products. On the reactant side, we have 1 iron and 3 chlorines. We also have 3 calcium and 2 phosphates. Notice I did not count the phosphorus and oxygen separate, and I just counted phosphate as a single unit. So I have 2 PO4s. On the product side, you can note that we have 1 calcium, 2 chlorines, 1 iron, and 1 phosphate. Looking at our chart or our pictures, we can see that every element is out of balance except iron. Let's begin by balancing the calciums. To correct the calcium imbalance, where I begin with 3 but only end with 1, what we can do is add a coefficient of 3 to our calcium chloride. So now that we have 3 calcium chlorides, that means that we have 3 calciums and 6 chlorine elements, as seen in the picture above. Since chlorine is out of balance, let's try and balance the chlorines. The least common multiple between 3 and 6 is 6. To make 6 chlorines on the reactant side, let's add a coefficient of 2. Notice how the coefficient adds another unit, but these units are identical. So now I have 2 irons and 6 chlorines. Notice that my irons and my phosphates are now out of balance. To correct my irons, I'm going to add a coefficient of 2 to the iron on the product side. This coefficient will mean that I now have 2 irons and also 2 phosphates. Now my equation is perfectly balanced. Notice there are 2 red irons on both sides. There are 6 blue chlorines on both sides, 3 green calciums, and 2 black phosphates. When looking at our chart, you can see that each element has the same number of elements on the reactant side compared to the product side. The next trick is called the water trick, where we're going to take water and rewrite it as HOH. By rewriting water as HOH, we're basically using the OH in water as a polyatomic ion to treat as a single substance. This will be really important in acid-base neutralization problems that we'll talk about later in the year, but we can still balance these equations now. We'll start by assigning symbols. So we can see that on the reactant side we have 1 sodium, and on the product side we have 2. On the reactant side we have 1 OH, and on the product side we're going to rewrite water as H and OH, so we also have 1 OH. On the reactant side, we have 2 hydrogens, and on the product side in water, we have 1 hydrogen and 1 hydroxide. And now we're going to treat carbonate, our polyatomic ion, as a single unit. So on the reactant side, I have 1 carbonate, and on the product side, I have 1 as well. So again, it's important that we not only make pictures, but we count up our elements on our chart. So as written, you can see that our imbalance lies between the sodiums and the hydrogens. So to balance the sodiums, I'm going to add a coefficient of 2 to the reactant side. Adding the coefficient of 2 creates 2 sodium hydroxides, meaning I have 2 sodiums and 2 hydroxide elements. Now notice that my hydroxides and my hydrogens are both out of balance. So to correct this, to add another hydroxide, I'm going to put a 2 in front of my HOH or my water. This 2 is going to make another water. Now you can notice in both pictures and numbers that the number and kind of elements on both sides of my reaction are the same. 2 reds, 2 blues, 2 yellows, and 1 purple. My reaction is balanced. The last balancing trick that I'll share with you is when an element appears in 2 different elements on the same side of an equation, balance that element last. This is very typical of both hydrogen and oxygen, so I always save hydrogen and then oxygen for last. Also, when counting the elements, keep the coefficients separate, as adding coefficients to one part may not affect the other part. Let me show you how. Sometimes you'll find that drawing an image is not the most efficient way to balance a chemical equation, but I will still use an image this time, though my preferred way would be to use the chart. So counting the elements on the reactant side, I see that I begin with 3 carbons, 8 hydrogens, and 2 oxygens, and I end with 1 carbon, 2 hydrogens, and for the oxygens, I'm going to write the coefficients separately. So I'm going to write 2 plus 1 oxygen. I know that 2 plus 1 is 3, but it'll be easier to keep count if I keep my coefficients separate. So here we want to save the hydrogen and the oxygen for last. So let's begin by balancing the carbons. To balance the carbons, I will add a coefficient of 3 to carbon dioxide. 3 carbon dioxides look like this. They have 3 carbons and now 6 plus 1 oxygens. So notice that I still have not combined my 2 oxygens found on the product side, as they have different coefficients. Last, we're going to balance the hydrogen. To balance the hydrogen, where I have 8 on the reactant side and only 2 on the product side, I'm going to multiply my product side by 4 to make 8 hydrogens. That will also, though, make 4 oxygens. Let's see what 4 waters looks like. So again, with 4 waters, you'll notice we have 4 oxygens that are red, and we have 8 hydrogens that are yellow. So now I see that my oxygens are out of balance. If I add the 2 coefficients, or the 2 numbers from the product side, the 6 and the 4, I will see that I have 10 oxygens. So to make 10 oxygens on the reactant side, I'm going to add the coefficient of 5. Let's see what this looks like in pictures. Now we have 10 oxygens. So if we examine the reactant side separate from the product side, you'll see that on each side we have 3 carbons, 8 hydrogens, and 10 oxygens. Here's 6 and here are 4 more. The most important thing to remember is balancing is tricky and time consuming. but you can do it. Take it step by step, and I know you'll find success. If you need extra support, please come to class with questions or go to lunchtime tutoring for extra help. So in case you struggled to balance the synthesis of ammonia, the first thing we're going to do is make a chart where we identify the elements directly below the reaction arrow. So reading from left to right, you can see we have nitrogen and hydrogen. Now we're going to count the numbers of each of the elements on both sides. Here you can see both nitrogen and hydrogen are out of balance. I always like to save the hydrogen and oxygen for last. So in order to balance the nitrogen, we're going to add a coefficient of 2 on the product side. That will give us 2 nitrogen. When you add a coefficient, make sure you simultaneously adjust the number of atoms in your atom count. So the coefficient of 2 changes the atom count on the product side to 2 nitrogen and 6 hydrogen. Now we need to balance the hydrogen. Since there are 6 hydrogen on the product side, in order to get 6 on the reactant side, we add the coefficient of 3. This concludes Lesson 38. Make sure you complete your homework, have taken neat and organized notes, and I'll see you in class.